orbital angular momentum should be taken as a base, and thereby it is possible to carry out these systems. Okay, in terms of Slater determinants. So very easily you can write the Slater determinants for either 2 electrons or many electron systems or up to the n electron systems. Okay, so here the wave functions should be always based on the Pauli's principle, should be antisymmetric. Okay, so if we talk about the antisymmetric or symmetric wave functions, it takes both the orbit functions as well as the spin functions. So how in these cases you have to take separately both orbital functions and the electron functions should be taken separately, and then you have to equate it. That is very important. So in the case of orbital functions, again you take the simple systems like many. In the case of many electron systems, the helium is the very simple system because it has only 2 electrons. Or we are assuming that it is a product of 1 electron into 2. Okay, so concerning the helium atom, the approximate orbital wave functions can be given as with respect to the electron can be present in either orbit 1 or orbit 2, that is pi 1 or pi 2. Okay, either it is the same or in terms of a different, etc. So in the case of the ground state helium atom means both electrons may be accommodated in the 1s orbital, and hence the configurations may be given as 1s2. Or if it is in the excited state means the ground state will be 1s. Okay, so the excited state will be the other one will be present. So it means that if it is in the ground state, okay, the orbit 1 and 2 means are same. The orbital wave functions 1 of 2 for the ground state is with respect to the electron 1 will be present in 1s1, and the second electron is present in so second one. So that is the cases. So if we interchange the 2 electron means thereby also there is no changes in the case of symmetric wave functions. That is, in the case of excited state, we can say that 1 electron is 1s and the other electron in the second orbital. Okay, so whereas in the ground state there is no change, only in the excited state it says that 1s will have 1 electron, and after 1s the second electron may be present in the next orbital like 2s. Okay, so the other in 2s orbital. So the configurations is 1s1 and 2s1. So the earlier previous, if it is a ground state, both electron is present in 1s2. Whereas if it is in the so in the case of the case of excited state, 1 electron is present in 1s1 and the other electron is present in 2s1. Okay, so here and the pi 1 and pi 2 are different. The earlier cases, both pi 1 and pi in the case of ground state, pi 1 and pi 2 are same. Whereas in the case of excited state, the pi 1 and pi 2 are indifferent. Okay, but the electrons are similar or indistinguishable, and orbital wave functions in the electron in the excited state is either it can be given as 1s1 or 2s2. Okay, because first electron may be present in 1s1 and the second electron may be present in 2s orbital, that is 2s2, or the second electron may be present in 1s orbital and the first electron may be present in 2s orbital, because the electrons are moving very fast and it is a very so it looks similar and indistinguishable. Okay, the probability must not change on merely interchanging the position of the 2 electrons, and thereby in conclusions the probability density are identical. That is the wave functions 1, 2 is equal to the wave functions 2, 1, or we can call it as a wave function of 1 of 2 can be plus or minus of 2 of 1, or that is a wave functions 2, 1 or symmetric wave functions or antisymmetric of 2 of 1. Okay, so the orbital wave functions, because here we have to, if you want to study about the symmetry or antisymmetry means we have to take into account of both orbit as well as spin. Okay, right now we are discussing when the electron is present in orbit like 1s orbit or in 2s orbit. Okay, so accordingly we are just studying. So the orbital wave functions must be symmetric or antisymmetric, and in the case of symmetric means how it can be means again you just use the same thing what we have studied in the case of Slater determinant, the same thing, that is n of 1s1 and 2s of 2. Okay, so in this case because it is in the excited state, 2 electrons in present in 2 different orbits, so 1s1 2s2, or plus 1s2 and 2s1. Okay, whereas in the case of antisymmetric, for one electron is present in 1s and the second electron is present in 2s, minus of 1s second electron and 2s of first electrons. And here it is, since it is we are discussing for helium, and n values or normalization constant values is 1 by root 2 or 1 by 2 factorial, root of 2 factorial. So antisymmetric with respect to interchange of the position of the two electrons is studied, and thereby the orbital wave functions of helium atom in the case of ground state is we can say that either 1s1 and 1s2. Okay, that is, it is symmetric in nature, whereas in the case the two orbital wave functions of helium atom in the excited state can be given as okay, psi of wave functions with respect to psi plus is given as a 1 by root 2 into 1s1 2s2 or plus 1s2 and 2s1. Okay, or with respect to psi minus 1s1 2s2 minus 1s2 or 2s1. Okay, that is with respect to symmetric and antisymmetric. Okay, so the helium atom has a one orbital wave functions. So we at last we can conclude here, like the helium atom used to have one orbital wave functions in the ground state and two orbital wave functions in the excited state, because we have taken both 1s orbit as well as 2s orbit in the case of excited state, whereas in the case of ground state we have taken only 1s orbital. Okay, so this is this is with respect to orbital wave functions. That is with respect to how the electrons is arranged both in ground state and excited state. Similarly, okay, right now we have to use the spin functions. As I told you, both we have to take both the electronic motions, means both orbital functions should be taken as well as electronic motion should be taken into account. Thereby, so right now we have to take the spin functions. Okay, again the same systems, the two electrons, and we have to calculate the spin functions with respect to, okay, so either it may be present in alpha form or in the form of beta form, the two electrons. So alpha of 1 or alpha of 2 with respect to symmetry in the excited state. Okay, so here you have to check how the electron is present in the case of alpha form or in the case of beta. So again the same thing, that is instead of orbital, here you have to take with respect to the electronic spin, that is 1 by root 2 into square bracket of, instead of 1s and 2s orbital or 1s or 1s orbital, here you have to give the electronic spin like alpha. Okay, alpha, either it may be alpha 1 or beta 2 or plus alpha 2 of beta 1. Okay, this is how the electronic spin, either the forward spin or the backward spin taken into account. Okay, so here there are there are symmetric, and we can call that there are okay, so three are symmetric with respect to, and one antisymmetric wave function is present, and it should be okay, always the complete wave functions must be antisymmetric based on the Pauli's principle with respect to interchange of every pair of electrons, isn't it? Okay, that is the cases. So we can check it for how the electrons is present in the ground state and as well as in the excited state. Okay, if you check the ground state, means it says that the wave functions, that is 1s1, and in terms of we have to take with respect to both the orbital and as well as spin functions. Okay, in the ground state, both the electrons may be present in 1s1 and 1s2, and that is with respect to orbit, and the electron spin is with respect to alpha 1 beta 2 minus alpha 2 beta 1. Okay, so this is with respect to, okay, that is one probabilities, and it says that A stands for a antisymmetric and S stands for symmetric in natures. Okay, so here when you multiply symmetric into symmetric, it will give the same values, because plus into plus same, whereas plus into minus, it is minus value. So symmetric into antisymmetric is antisymmetric, or antisymmetric into symmetric also antisymmetric, whereas minus into minus is plus. Okay, either symmetry into symmetry or antisymmetry into antisymmetry, both will give you the symmetry value, and the product of plus into minus or minus into plus will give you the antisymmetric images. So likewise, if you check it out